Let's start with our lesson today. Today we will cover 9.3, confidence interval for population variance. Now, you will see that the procedure to construct this confidence interval is different from the ones we did before, confidence interval for population proportion, population mean. Now, that is because the sample variance is not a robust estimate for population variance. Now, what does it mean to say robust estimate? This is the reason. This is what it means. When we say population mean, sample mean is a robust estimate for population mean, we are saying that even though sample mean may not be an accurate estimate for population mean, but the error will decrease as the sample size increases. Remember the margin of error, E equals to the critical value times the variance over square root of n, right? Now you see as n gets larger and larger, the margin of error gets smaller and smaller, right? Now the same case with our population proportion. Sample proportion is a robust estimate for population proportion P. Sample proportion is a robust estimate for population proportion P because if you want to be more and more accurate, then simply increase the sample size. Okay. Now the thing is that is not true for sample variance. We can increase the sample size, yet the sample variance get even further away from the population variance. Okay, so while we will still use this sample variance as our point estimate, I even use quote unquote for the word point estimate here, because that's not the word, that's not the phrase we're supposed to use. It will not be in the middle of our resulting confidence interval. Now, you see that when we construct confidence interval for population proportion, notice that the sample proportion is in the middle of the resulting confidence interval, right? Okay, the best point estimate, you add and subtract margin of error. So what happened is the best point estimate P hat, the sample proportion, must be in the middle of that confidence interval. Likewise, for sample mean, we add and subtract margin of error such that the confidence interval that we get will have sample mean right in the middle of that interval. Now you will see later on that our resulting confidence interval for sigma squared or population variance will have this kind of situation. So the sample variance will not be in the middle. It tends to be on the left-hand side of the resulting interval. Okay, now the formula will later on be, I'll give you the picture first, then the confidence interval we get later on will be n minus 1 times s squared over chi squared right. That's the lower bound of that resulting confidence interval. Okay, and the upper bound will be n minus 1 times sample variance over chi squared left. Okay, that's the confidence interval we are trying to construct for this population variance. Again, that sample variance S squared is not right in the middle. It is not right in the middle. So another way to say that, if, for example, if somebody give me confidence interval for P, as the confidence interval for P is between 0.3 and 0.7. Now I can find your sample proportion from here. Your sample proportion must be the midpoint. I can reverse engineer that. Okay. Now that is not the case for confidence interval for population variance. No way. You can give me confidence interval for population variance from, let's say, 0.3 to 0.7, and I have no way to catch it back. I cannot, there's no way for me, to find what is your sample variance from there. There's no way. Okay, there's no way. Now, let's see the formal procedure, at least the template to construct confidence interval for population variance. That will be, the first step, we'll find chi-squared right. The second step, we'll find chi-squared left. The third step is the confidence interval, so we will do the declaration first. Okay, and the formula will be degree of freedom times sample variance over chi-squared right less than sigma squared less than degree of freedom sample variance over chi-squared left. That's the template. Okay, now what is chi-squared distribution? Chi-squared distribution is a non-negative skewed to the right distribution. It is not symmetric. It looks like this. It looks like this. It's non-negative and skewed to the right. Okay. Non-negative means the curve is always on the first quadrant. That's one. Second, it is skewed to the right, means like this. If it is symmetric, then it would have looked like this. It would have to look like this. If it is symmetric, you see? It would look like this if it were symmetric. But no, it's not symmetric. It's skewed to the right as if the right tail here is being pulled further to the right. That's what it means to say skewed to the right. Now, because of the fact that it is not symmetric, because this curve is not symmetric, then when we say, let's say 95% confidence level, we still have that 95% area in between, but it is not right in the middle. Okay. Now the remaining 5% will be shared by two tail. Okay, such that the area for each tail is 2.5%. So you still have 95% in the middle of that curve, but not really in the middle exactly like in case of the symmetric distribution. No, it's in between to be more precise. Okay, but it's not right in the middle. No. Okay, now the remaining 5% is still being divided by 2 tails. Now you will see that the tail here is shorter from 0 to whatever number that is. The tail there will be shorter. The tail here will be longer. You see? Okay. But of course, the area is still 2.5. The area is still 2.5%. Okay. Which means the area on the left-hand side is bigger. The height, it's taller because the area is the base is smaller, while the one here is shorter because the base is longer. Okay, well, anyway, we don't go into that region. Now, when we say chi-squared right, it refers to this critical value, chi-squared right, and this one is chi-squared left. Okay. Now, how do we write that chi? We write it down as chi, C-H-I, okay? But the way we write it is this, like the main diagonal is curvy, okay? Now, the other diagonal is straight and shorter. That's how a chi distribution written. Now, why do we have that square, Thomas? Now, don't ask me. Don't ask me why they put square there, but I believe that's I know that's the reason. The reason is because they want to emphasize that this distribution is non-negative. It's always square. It's always 0 or positive. Can never be negative. Okay. Now that also means later on your chi-squared critical value, chi-squared right or chi-squared left, always have to be positive numbers. Okay. Now, if you happen to be a Christian, now the Greek letter for Christ, that's why we chi like that, Christ. Okay, Christ. The chi that is used in Greek letter is this chi. Okay, it's that chi. The Greek letter for Christos, Christ in Greek, as I remember, is this Christos. You know, that's the chi being used. Okay, now it's not about the Christ or being Christian, it's about the letter. Okay, yeah, and some background, like why we read it as chi while it looks like an X. You know, it comes from the Greek letter of chi. Okay, now, so the thing is, since 2 years, 3 years ago, I have decided that my class will not use table anymore. So I need you to have programmed your calculator with inverse chi distribution. With inverse chi distribution. Now I already did. How about you? I mean, I did mine since last year. I have inverse chi distribution. Now, if you have not programmed yours, please go to our discussion board and watch this video here. This is not from me. This is not from me. I think if I do the programming and I video that, I cannot do better than her. Okay, so this lady actually did a very, very good job, in my opinion, in teaching us how to program that. Okay. Now, let me start first. Any of you have not programmed this? I mean, if you need time to program this, I will give you 15 minutes, then we come back working on that, on the rest of this section. Okay, but I rather you watch the video and program that Okay, 5 minutes should be enough, but if you need more time, I think 15 minutes is more than enough. Anybody have not done that? Let me know in your chat if you have not. Otherwise, I will go on. Okay, everybody's done, right? Okay, everybody's done. Let me see. Now, if everybody's done, then let me see. How to get to it? You go to program. Give me a second. Yeah, so you go to program. Okay, so let me quit first. So this is where we start, right? You click program, then you will see inference Kai there. Anybody else not done yet? Because once I start, I don't want you to tell me later on, oh, Thomas, can you tell me how to program that again? I would be so pissed off. Okay, give me a second. Okay, so I assume that you are all already done with the programming. So let me continue then. Now, I will perform on the template first. Okay, like for example, let n equals to 34 and the confidence level is, let's say, 95%. Now these are the information we need in our step 1 and 2, finding chi-square left and chi-square right. In our step 3, then we will need the sample variance to be S squared to be, let's say we make it 3.45. Okay, again, for your step 1, we need these two numbers. We will 1 and 2. Step 3, we'll need this. Okay, and then construct confidence interval for population variance. Okay, step 1, chi-squared right. Sketch the graph first. Okay, for chi-square distribution, it will be non-negative skewed to the right graph. Now then, we need 95% in between such that the area of the area two-tail will be 2.5% each. Now, chi-squared right is the critical value such that the area to the right. Now, this is the one you may not like, I believe, and I don't like this either, but they have their own reason doing it this way. When you use calculator for chi-squared right, it's not like before we get the area to the left instead, the cumulative, right? Okay, or when we did inverse t, let me show you. Now, when we did inverse t, I wonder if you remember, inverse norm and inverse t, when they say the area, it is always area to the left, right? Okay. Now, that's not the case for critical value in chi-square. Okay. Now, when we use to find critical value in chi-square, then the area, always the area to the right. Okay. It's always area to the right. Now, so when I need to find the chi-squared right, the notation will be, the calculator notation first, it will be ins chi. Now, the first number is area to the right, 0.025. This is area to the right. And then the second number is the degree of freedom. in this case is 33. Okay, so if I go back to my calculator, area to the right is 0.025. That's 2.5%, right? Now then, what is the degree of freedom? Degree of freedom always, in this class, is always 1 less than the sample size. Then I will get 50.72508. That's 50. 50.72508. Okay. Now that's chi-squared right. Now how about chi-squared left? Chi-squared left is this guy here. It's this guy here. Maybe I use yellow. It's this guy. This is chi-squared left, such that the area to the left is 0.25. But if the area to the left is 0.25, what will the area to the right? The area to the right will be that 95% plus this 2.5%. Okay, that's 97.5%. You see what I mean? So the calculator notation will be inverse chi. Area to the right is 0.975. And degree of freedom is 33. Okay, I will call that program again. Once you click that inverse chi, you will see this. You need to press enter again to start the first question. Area to the right, 0.975. Degree of freedom is 33. Okay, it's 19.04666. 19.04666. Okay, now you will see the following, that the peak here, which is not the symmetry, okay, that's not the symmetry. The peak here will be approximately equal to the degree of freedom. Approximately equals to the degree of freedom. Now, what I mean then, this chi-square right must be greater than degree of freedom, and chi-squared left must be less than degree of freedom. Okay, so if you see on this number line here, this will be 19 something, right? This is 33. This is 50 something. You see that? Okay. Now this kind of nature, this kind of observation, will be great for you to detect if you happen to get a wrong number. You know, like you and I may punch something wrong to our calculator, right? And then we get different number. Okay, so have this kind of observation. Okay, the peak will be approximately equal to the degree of freedom. Okay, to be honest with you, I forgot, is it precisely equals to the degree of freedom or around degree of freedom? Somehow I think the peak supposed to be equal to the sample size. Again, I forgot. Okay, or maybe the peak is degree of freedom or between these two numbers, but doesn't matter. We are sure that the chi-squared right has to be to the right of degree of freedom. Chi-squared left has to be on the left-hand side of degree of freedom. Okay, now once we are done with this chi-squared left, chi-squared right, then declaration 95% confidence interval for population variance is given by degree of freedom n-1 times sample variance 3.45 over chi-squared right less than sigma squared less than degree of freedom times sample variance over 19.0466. Okay, now then you use your calculator. Unfortunately, there is no calculator program for us to use to confirm our answer. It's not like we can confirm our answer like when we construct confidence interval for population proportion P or population mean mu, right? Now for this one, no, we don't have formula for this. I mean, we don't have calculator function for that. This is 2.24445. 2.24445 less than sigma squared less than 33 times 3.45 divided by chi-squared left, 19.04666. That's 5.9774. 5.9774 what? 425, let's call it 3. Okay, so the key is really the first two here. You need to know how to find the critical values. Okay, there are two critical values that we need to look for, not like in the previous cases. We have two critical values and you use both of them in the formula. And keep in mind, chi-squared right, the first number, chi-squared right, will be on the denominator on the left of that inequalities. And chi-squared left will be on the denominator of that inequality. Okay. Now, if you happen to reverse the order, the red, the yellow and the blue, you will see this number here is larger, this number here is smaller, which doesn't make sense. Okay. So chi-square right is greater, right? Now you will divide by a greater number here such that the quotient is smaller. Okay. Chi-squared left is a smaller number. Now you will divide by a smaller number such that the quotient is larger. Okay. Now let me go on some follow-up question before we do other problems. Sometimes our textbook or the problems want us to go on with construct. Let me use blue, green color instead. Construct confidence interval for sigma. If the question is construct confidence interval for sigma, then you will basically do exactly the same procedure, but then you do one extra step, step 3, one more time. But this time you will apply square root to both sides, to 3 sides. Okay, don't forget, you still need to declare again. Okay, still declare again, but then you provide square root on each side of that inequality. Well, because sample standard deviation is square root of sample variance, right? Standard deviation is square root of variance. Okay, let me do the square root here. That's 2.44488. So this is 2.44488. And the square root of 2.24445 will give me 1.49815. 1.49815. Okay. That's one template. Now, sometimes when I explain some procedure, I really want to explain the background of that formula, that procedure so much, so what happened here again, the sample variance is not the best point estimate, okay? In fact, it's not even a point estimate, okay? Such that our sample variance will not be located right in the middle of the resulting confidence interval. That's one. Okay, that's one. The chi-square distribution itself is not symmetric. It's skewed to the right. And that's another reason why the resulting confidence interval should not be symmetric around the sample variance. But more things to say about this topic here. Maybe I use in red notes. Okay, this is a big note. Okay, first one. This procedure comes from, I think I better say, does not come from central limit theorem, even though related to it. Okay, it does not come directly from central limit theorem. Okay, however, it relies on an assumption that the underlying population, the population you took the sample from, is strictly normal. It has to be normal. Any deviation from normality will make our confidence interval that we get here is incorrect. Okay, so the underlying population is strictly normal. This is not the case for the other, this is not the requirement for other situation. This strict normality was not required for confidence interval for P nor X bar for mu. Okay, the requirement confidence interval for P, the requirement is actually that NP and Q, I'm sorry, NPQ, that's our textbook, NP hat, Q hat, has to be at least 10. Now, confidence interval for mu, then the requirement was that the N is at least 30, or the underlying population is approximately symmetric. Okay, the closer the underlying population to be normal, the better it will be, the result. Okay, but no, there's no such strict requirement that it has to be normal. As long as it is symmetric, it's okay. As long as it is almost symmetric, it's okay. Okay, now and then confidence interval for P, as long as the sample size is big enough such that this requirement is satisfied. Okay, but confidence, when we construct confidence interval for these population variance, the underlying population has to be strictly normal. It has to be normal. Okay, now for that reason, for this reason, many universities including the Ivy League school do not teach this procedure, this topic in their first or second year statistic, elementary stats. I can even say that most universities do not teach this. Why? Because the requirement is so strict such that in almost no case we can really really apply this unless the population is known to be normal. Okay, I mentioned this because the following. Notice that our college, just like a lot of colleges in Southern California, even in California or in the United States, we tend to not to teach material. We tend to cut off material or topics that we're supposed to teach. Okay, let's say universities teach, let's say the topics A, B, C, D, E. We end up teaching only A, B, C, D, you know, okay? We tend to teach less than what universities requires. Okay, now, but for example, Bayes theorem. Bayes theorem is one thing that university teach, but we don't. On the other hand, this material is the material that we teach in college level statistic. Like not only West LA College, but also at East LA College and also at Santa Monica, as far as I know. Okay, we teach this topic, but this topic is actually not being taught at UCLA, UC San Diego, UC Berkeley. I know for sure not in Harvard, not in MIT. Not in University of Washington, not in Brown University. Okay, a lot of universities actually don't teach this material, but it is taught in college level. Okay, now, why do I mention this? Not because I agree with the college. I mean, they tell me to teach something, I teach it. Okay, that's not an issue. Okay, I just want you to be aware that this model is not a model you can apply easily or casually. No, you need to pay attention to the normality of that population. Okay, you need to make sure that the population that you get the sample from is strictly normally distributed. Okay. Secondly, because of this reason, the second reason that most universities don't teach this, then when you transfer to university, okay, we usually do not compute or do confidence interval for population variance and therefore population standard deviation. And it is not something they assume that you know. Okay. And they don't assume you to know, not because they think that you are not able, but it requires a much higher statistical skill to confirm that the underlying population is normal. Not even almost normal, no. Not even nearly normal, no, it has to be normal. Okay, any deviation from normality will result in very unreliable confidence interval. Okay, and again, this confidence interval, if you look into this, right, if you look into the formula, notice that the n-1 is on the numerator. You know what it means? The larger the sample size, this guy will get larger. This guy will also get larger, right? You see? Remember I said earlier that for this model, the larger the sample size, your sample variance may get further away from your target instead. Okay, and it is being reflected in the formula, right? Imagine if your n is from 100 becomes 1000, it gets a lot larger, right? Right? This number gets larger and this gets larger too. Okay, now let's apply this idea into this template back into our some questions. But you will see that because of this fact, I personally, just like our textbook, if you see, have hard times to get problems, real life problems, because most universities don't teach this. So I myself, if I try to copy paste problems from universities, I don't find it in their old tests. Okay, well, anyway, let's start again. I will do one more and then I will ask you to do a couple questions from our textbook. Okay, let's say n equals to 48. Confidence level, 98%. And then sample standard deviation is 2.7. The question is construct confidence interval for population standard deviation. So step 1, I need to do chi-squared right. Step 2, I need to do chi-squared left. Sketch the curve for chi-square distribution such that the area in between is 98%. The remaining 2% will be shared by two tails. So 1% for each tail. This is chi-squared right. The area to the right is 1%, right? Okay, so calculator notation, inverse chi, the area to the right, 1%, degree of freedom, 47. Okay, now then I use my calculator. Program inverse chi, area to the right 0.01, degree of freedom 47. Now, before I press enter, I have one more thing to say. Notice that what I show you here is the calculator. Actually, it's an emulator. The calculator that emulate what you see on your actual TI 84, right? Okay. Now, do you mind to punch this in? And then we press enter together. Let's do it in 3. 1, 2, 3. Okay, you will notice that my computer calculator is getting the result faster. It's like in 1 or 2 seconds. Your calculator may take up to like, may even take like 15 seconds, half a minute. It's possible. Okay, now you will see the following. Let me repeat that. Area to the right, 0.01. Degree of freedom, 47. Now you will see that your calculator is still thinking if there's something moving here on the top right corner. Okay. It's so fast for my calculator so that you don't really see that though. But you know that your calculator is still working on that. Okay. If after you press enter, you don't see anything coming out, but you will have some like little dots here keep on moving up and down like that. Okay. It will take like around 5 seconds, maybe 10 seconds. I have been in a case where we needed to wait it for 20 seconds. I never had the case of 30 seconds though, but I have had the case, I myself had the case when I use my handheld calculator, TI-83, the one I use, it takes so long to get the result. Okay, but if you have that situation, the reason I tell you this so that you know that, oh, you are not, it's not that something wrong with your calculator. No, it does take long time for your handheld calculator to compute that. Your calculator does not have that Intel Celeron that's going fast. No, the processor on your calculator is a slow one. Okay, and I hope you understand why they don't put this function into our calculator formally. It will slow down the calculator by big time. Okay, so it does take some time. Now, chi-squared left, that is this guy here, chi-squared left, such that the area to the right is 98%. That's the BOM, right? That's the confidence level, plus the 1%, one of the tail, a total of 99%. So this is inverse chi, 0.99, degree of freedom 47. Now this number has to be less than 47 later on. Okay, when I plug that in, program inverse chi, area to the right 0.99, degree of freedom 47. The number has to be less than 47. This is 27,41585. 27,41585. Then step 3, 98% confidence interval for sigma squared. That is degree of freedom times sample variance. Don't forget to square it because that is sample standard deviation, right? That 2.7 is sample standard deviation. So I have to square it to make it sample variance over chi squared right less than sigma squared less than 47 times 2.7 squared over chi squared left. Now using my calculator, 47 times 2.7 squared divided by 72.44331. It's 4.72963. 4.72963 less than sigma squared less than 47 times 2.7, that's sample standard deviation. I need to square it to make it variance. Divided by 27.41585. That's 12.49752. 12.49752. Now that's the confidence interval for sigma. What they want is confidence interval for sigma square. What they want is for sigma. So we go on 98% confidence interval for sigma. Then I will do the square root for 4.72963, 2.17477, 2.17477, is it right? Less than sigma less than square root of 12.49752. 3.53518. 3.53518. Now, there's a reason why we need to separate the confidence interval for sigma squared from confidence interval for sigma. Now, remember that we say that this is already kind of like require a very heavy strict normal distribution in the underlying population, right? Now, when you apply square root, this may not be what the target we want. In other words, while assuming normality, when we assume normality, sigma squared is in, we have 98. How to say that? When we apply square root, right? When we apply square root for this interval here, this gets less reliable. Okay, the way we construct the confidence interval, this template is actually designed for confidence interval for sigma squared, not for sigma. Our textbook going on saying that, okay, if you want to get the sigma confidence interval for sigma, just square root all three terms, all three sides, the left-hand side, middle term, and right-hand side. But actually, the result is actually getting less reliable. Okay, that's why then the confidence interval has to be declared, the one for sigma squared, and being declared again for sigma. Okay. This model is how to it's a, I don't want to call this a headache. The idea is actually quite simple. For the purpose of answering question, this is easy to do. In reality, in actuality, this procedure is hard to apply. Okay. Even before this, even before you start with step one, you need to check a lot of things. You need to check the normality. That's why. Okay. Now let's pick a problem or two problems from our textbook and let you do that. Okay, give me a second. Where's my book? This is chapter 9. Let's do number 10. Okay, let me ask you to do this. A simple random sample of size n is drawn from population that is known to be normally distributed. The sample variance S squared, oh, that's nice. They give you the S squared is 19.8. So S squared equals to 19.8. Now part A, construct the confidence interval for sigma squared, confidence level 95%, sample size is 10. Okay, let me give you around 5 minutes to do that one, and then I will check you back. Okay, right now it's 4:57. I will go over this at 5:03, around 5 something minutes from now. Okay, do your step 1, chi-squared right, and your step 2, chi-squared left. Don't forget you need to first write the calculator notation, then the result from calculator notation, then result from calculator. Step 3 later on, 95% confidence interval for sigma squared. Okay, let me ask you to do that. So we have standard normal, we have chi-square distribution, 95% in the middle means the remaining 5% being shared by two tail, chi-squared right, have area on the right-hand side, 2.5%. Degree of freedom, 9. So I use my calculator to compute that. I will use my handheld calculator now. I get 19.02277. You notice that I have a pause for like around 10 seconds earlier, 7 seconds, I guess. That's because I was waiting for my handheld calculator to give me the result. That's how long it is. Yeah, compared to if you use computer. Inverse chi of, what is the area on to the right-hand side? That's 95% plus 2.5, so 0.975. You will notice that if you add these two numbers, they're supposed to be 1. Yeah, that's supposed to be 1. Okay, so then I start the program again, and you will need to wait for around 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 9 seconds. 2.70039. Okay, so how about the confidence interval then? It would be 9 times, what is the sample variance? 19.8. 19.8 over chi-squared right, 19.02277 less than sigma squared less than 9 times 19.8, not 19.9, 19.8 over 2.70039. 9 times 1.9, 19.8 divided by 19.02277 is 9.36772 less than sigma squared less than 65 something. Okay, that's what I get. Anybody can confirm? Do you get the same thing? Or near this number maybe? Okay, good. Now let's try part B. Basically the same procedure, right? This time we change the sample size to 25. The purpose is we want to see how does increasing the sample size affect the width of the interval. Okay, the width of the interval here is approximately 55. Width is approximately 55 or 56 actually, right? Okay, but what happens if we increase the sample size? Okay, now let me ask you to do that again. The same informations except that the sample size now changed from 10 to 25. So that's for part A, part B here. You don't need to do part C, just do part B. So the confidence level still the same, 95%. Okay, but because the sample size changed from 10 to 25, so the degree of freedom will also change, right? The degree of freedom later on for these will be 24. Okay. And again, the sample variance is 19.8. Let me give you 5 more minutes to do this. Yeah, let me give you 5 more minutes to do this. So right now it's 5:08. I come back at 5:13. Okay, let's start. So step 1, chi-squared right will be inverse chi, area to the right, 0.025, degree freedom 24. Weighting chi-squared left will be inverse chi, 0.975, 24. On the top one, I get 39.36408. So you see that while I was waiting for this one, I start writing this already, you know. Okay, now you don't need to do it in rushing like what I did though. Okay, I just try to say that for me to wait for this number, I have enough time to write this one line here. Okay, now then inverse chi 0.975, degree of freedom 24. This is 12.40115. So this will be 24 times 19.8 over 39.36408 less than sigma squared less than 24 times 19.8 over 12.40115. That's 12.07192 less than sigma squared less than okay 38.31903. Oh, you see that the confidence interval is actually smaller now, huh? Narrower. The width is approximately 38 minus 12, that's 26. Here, the width is approximately, what's that, 67 minus 10, 57, approximately 57. So in this case, the confidence interval gets smaller that gets narrower. Okay. I will stop here for this section. Part C, which I will not answer. The question is like, construct 99% confidence interval. So if you increase the confidence interval level, the confidence level, and holding the sample size the same, 10, what will happen? As we expect, the confidence interval will get wider if the confidence level is higher. Okay. The confidence interval will be wider if the confidence level is, so basically the width will increase as confidence level increases. Okay. Now that's for 9.3. Now let's go on with the later part. I want to go over one old test, the one that I showed you last time from fall 20, right? Fall 20, Math 227. Give me a second. I quote that in. Test 3 in class. There are 7 pages, 8 pages together with the supplement. So this is fall 20, Math 227, test 3 solution. Now I want you to be aware that I already post the full solutions actually on the discussion board. Yeah, on the discussion board, if you see, this is the one we'll go over, and hopefully we have time to go over this also. Okay, but this is a solution. Okay, this is the solution. So in fall, I give the test, which is the same test I gave in summer. Now, let's start. Let me close some windows first. I will use blue color. Number 1. Weights of bags of goodie cookies have normal distribution with mean 16.2 ounce and standard deviation 0.8. A box contains 12 bags. So X be weight of a bag that is normally distributed with mean 16.2, standard deviation 0.8, so the variance is 0.8 squared. Now, part A, what is the probability that a bag of goodie cookies is less than 16? Probability that X is less than 16. That's normally distributed, right? That's normal CDF. The lower bound is negative E99. The upper bound is 16. The mean is 16.2, standard deviation 0.8. Now use your calculator. I get 0.40129. Now always write the probability notation, then calculator notation, then calculator result. Okay, you need to have those 3 ingredients. Don't try to skip steps though, because this is part A. If you already start skipping steps, then imagine what happened with part E. Okay, if you don't know how to frame, writing the notation properly helps you framing your thought. Instead of jumping to the answer right away, you rethink about what we need to look for first. We need to achieve first. Okay, that is true in my class. That is also true in your life. If you have problem, okay, instead of reacting right away, if you have problem in your life, instead of reacting right away, instead of panicking, okay, sit down first, think about, conceptualize, think about the problem that you face first. Okay, 95% of all bags weigh more than K. So probability that the weight of the bag more than K is 95%. Right? Okay, pictorially on our normal distribution, 95% weigh more than K. If this is K, then the area to the right is 95%. Okay, but we cannot compute that using our calculator because our calculator can only do the one on the left-hand side, area to the left. So I need to reverse the order of my event. The area to the left of K instead is 1 minus 0.95, the 5%, right? The remaining 5%. So K will be inverse norm, area to the left, 0.05. The mean is 16.2, standard deviation 0.8. Now, this kind of notations you will not memorize if you don't practice enough. Okay. But Thomas, it's open book, right? It's open notes. I can just look at my notes. Yeah, well, if for every question you need to look at your notes, then 2 hours will not be enough. Okay. In fact, not only that 2 hours will not be enough. Even if I give you 3 hours, which will be the case for your test 4 and final, your brain power already shut down. Basically, if you think your brain has a battery, okay, the way you work is so inefficient such that by the time you will reach 2.5 hours thinking hard, your battery already gone. You already give up. Okay, so no, it's not a good idea though. Okay, it's not a good idea to think that, oh, I have the notes, so I don't need to study before the test. I can just study during the test. Nah, no. Whoever thought that way, none of them make it. Okay, and please try to follow me. Please try to do this also, just in case I make mistake. Okay, but for part B here, it's finding the cutoff score that separate the top 95% from the bottom 5%. Part C. No, part C here. Part C is up here. A box, which is 12 bags, is selected at random. Find the probability that the weight of that box is more than 200 ounces. Box is not a bag. Okay. Probability that the box is more than 200 ounces. But the box has 12 bags, right? So it's the same to say the probability that the average weight of those 12 bags is more than 200 over 12. Do you see that? Even though the question is in terms of the total, you can answer that in terms of the average. Okay, this will be normal CDF 200 over 12. That's the lower bound. Upper bound is E99. The average for the sample means 16.2. The standard error, however, is 0.8 over square root of 12. Okay, that's because X bar 12 is now normally distributed with the mean, the same mean, yet standard deviation is 0.8 over 12. So the variance is 0.8 squared over 12. Normal CDF 200 over 3 up to infinity. The mean 16.2, standard deviation 0.8 over square root of 12. So the probability is 0. Under no situation, the weight of that box be more than 200 ounces. Did I punch anything wrong? Oh, yes. I punched something wrong. No. I punched something wrong. My bad. I divided by 12, by 3 instead of by 12. 200 divided by 12. And then E99, 16.2, and 0.8 over square root of 12. Oh, this is better. 0. It's small number, but I didn't expect that to be 0. 0.02615. That's what I get. Let me check my coding again. Yeah, that's right. Yeah, earlier when I punched in my calculator, I wrote 3 here. I typed 3 instead of 12. That's why it becomes very, very small. 0. Yeah. I know the answer will be 0. I didn't expect that to. I know the answer will be very small, but not 0. Part D. Now, a bag is selected at random. Find the probability that half of those 12 bags. So this is the number of bags. Okay. Let Y be number of bags with weight more than 16 ounces. Now this Y will be binomially distributed. This is the number of bags, not the average of those 12 bags. No, that's of these 12 bags. What is the probability? What is the probability that at least half of them have that weight more than 16 ounces? So there are 12 trials. The probability of having weight more than 16 was computed earlier in part A. That's the probability for one bag to weight. Actually, that one for less than 16. So for more than 16, this will be 1 minus 0.40 something. Let me see. 129. Okay. Let me give a notation. This is the probability that x less than 16. That's from part A. Okay, that's from part A. Now then, what is the probability that at least half of them? So Y is at least 6 having the weight less than, actually having the weight more than 16. That's 1 minus probability that the number of bags to be at most 5. That is 1 minus binom CDF, number of trials, 12. This is, you can just put in 1 minus 0.40129 up to 5. You can do that. You can do that. You can try using your calculator. normal CDF, binom CDF. Okay, the number of trials is 12. Probability of each success, probability to have weight more than 16 will be 1 minus 0.40129. And then up to 5 such bags, I get 0.16050. Okay. Now let's see part. Where's the, give me a second. Let's see part E. My computer gets slower. I wonder why. What happened? Yeah, part E. If the average weight of 12 bags is at the bottom 10%, what is the maximum average weight does those 12 bags have? Oh, you know what? I think I make a mistake on my calculator here. No, this is not right. I miss one minus. That's 0.16050 is the result from binom CDF. I have not subtracted it from one. 0.8395940. Okay, that's the correct answer. I forget that one minus. Okay, part E. If the average weight of 12 bags is at the bottom, so we have 12 bags, that's X bar 12. It is at the bottom 10%. So this is 10% here. At most, what is this? That's the one in question. So probability that the average weight of those 12 bags to be less than equals to K is 10%. What is K? Now we know that X bar 12 is now normally distributed with mean 16.2 and variance 0.8 squared over sample size 12. So K will be inverse norm 0.10. The mean is 16.2. Standard error 0.8 over square root of 12. I get 15.90434. Okay. Part F. A consumer advocacy inspector will take a random sample of 10 boxes, not 10 bags, no, 10 boxes. 10 boxes, and sue the company if the average weight of these boxes is under the weight claimed by the label of the boxes. So what is the sample size, by the way? The sample size will be 10 times 12. That's 120. That's the sample size now. Okay, so on your bag, they claim this is the weight. Okay, now of course, even though they claim the weight is something, there's a chance that the weight is actually more or less. Now, the company is willing to run the risk of being fined 2% of the time. Then what the label supposed to say? Okay, you need to find the hint. It's like let K be the claim weight. You need to find the K such that the average weight of 10 boxes is less than K is 2%. The average weight of 120 bags is less than 2%. Find what will K be. Okay. Actually, hold on. What weight should it label the boxes? Oh, the boxes, not the bags. Okay. Okay, let's compute first. What should that label the bags? So this is K, let's call it K1, is the claim weight on a bag. This is inverse norm 0.02. The mean is 16.2. Standard deviation, standard error is 0.8 over square root of 120. That's 16.050015. Okay, so let K2 be claim weight on a bag, on a box. Which is 12 bags. Okay, so K2 will be 12 times K1, which is 12 times 16.050015. Okay, I get 192.60018 ounces. I think it's fair enough to say 192.6 ounces. Okay, but in my class, since we do 5 decimal places, then we leave it like that. Okay. That's for part F. Let's go on to the new question. I will do number 2, and after that, I give myself a break. Number 2, a computer manufacturer has its chip supplied by supplier A and B. After testing the chips, 7% of them are defective. So defect, 7%. Good, of course, is 93%. Now, furthermore, 45% of defective chips and 40% of effective chips are from supplier A. So the defect one, of those defect, 45% of them from A. For the good one, 40% from A. The remainder supplied by B. So of those defect, 55% from B. Of those good ones, 60% from B. Find the probability that a randomly selected chip is from supplier A. Probability that it is from A is equal to probability that it is defect N from A plus probability that it is effective, or we call that good here, N from A. So basically, to get a chip from A, it's either this path or this path. Okay, now then that is equal to 0.0, maybe I write percentage first. That's 7% times 45% plus 93% times 40%. That is equal to 0.07 times 0.45 plus 0.93 times 0.40. That is 0.0315 plus 0.372. This is 0.4035. That's the probability that the chip is from A. That's the probability that a chip is from A. Now, part B, of 100 chips from B, find the probability more than half of them are defective. Ooh, okay. Well, what is the probability it is from B to start with? Probability that it is from B is equal to, you have two ways. Either you do probability that's defect plus intersection D plus probability that it is good intersection B, similar to what you did in part, oh, is there part C somewhere? No, I think I happened to, oh, skip. What is the probability? I'm sorry. I need to go back to C. Find the probability that a chip from B is defective. Probability a chip from B is defect. That's equals to probability, I write it wrong, sorry, it's defect. Probabilities that defect N from B over probability from B, is it right? But probability from B and defect is this one, this guy. 7% times 55%. That's 7% times 55% over probability from B. But we know if the chip is not from A, it must be from B. So I can just use 1 minus 0.4035. Okay, this guy is from part B. Okay, now then when I compute this, this is equal to 0.07 times 0.55 over 0.5965. That's 0.0385 over 0.5965. That's 0.06454. That's the probability that a chip from B is defective. Okay, let me write a little note here. Probability A plus probability that B equals to 1. The chips are from A or B. It means the proportion of chips from A plus proportion of chips from B should be equals to 1. That's why we can use that here. Okay, now part D. Of 100 chips from B, find the probability that more than half of them are defect. Let X be number of chips from B that are defective. Now this X will be binomially distributed. Number of trials, there are 100 chips. Probability for each chip from B to be defective is, what's that here? 0.06454. 0.06454. Okay, now what is the probability that more than half, X is more than 50? That's 1 minus probability that X is at most 50. 1 minus binom CDF 100. I need some space. Let me move them to the left. Zero point 0.0645450. That's 100. The P is 0.06454 and up to 50 is 1. So the probability that more than half of them from B is actually 0. I'm sorry, probability that more than half of them are defective is actually 0. Okay. In fact, what is the average? The average is N times P, right? So you expect, if you have 100 chips from B, you expect around 6.5 of them, around 6 or 7, maybe 8, maybe 9 of them are defective. But it won't be more than half. It won't be more than half. Okay, now part E here is actually a new thing. I think at that time it's something recently, something I put in my test recently. Okay, complete the following contingency table corresponds to the situation above. Basically, I want to relate our probability tree and contingency table. Okay, now the total is supposed to be 100%, right? Okay, now what is the probability that a randomly, so we need to fill this up here. Okay, now from part B, we know supplier A, right? That total should be 40.35%. Is it right? Okay. Now, then, of this 40.35%, what percentage actually defective? Defective is this one here. That's 3.15%. And effective one is 37.2%. See, if you don't show your work, the reason I asked this part E, because I have seen students, when they did questions from A, B, C, D, for example, they skip the computation a lot, such that they don't even realize they already make mistakes. Okay, so the purpose of this part E is actually summarize again what you actually know. Okay, now, by the way, the percentage that's defective, actually we know that it's defect 7%. The defect is 7%, right? 93% are good. Okay, so from here we can actually complete column B without going further. Okay, so for example, 3 something plus what give you 7 something, that must be 3.85%, right? Defect N from B happens to be computed somewhere in between. Okay. And how many from B? How many from B? Well, what adds up to 100% here? You need to add 59 something. That's 59.65%, right? Which we happen to compute already here. Okay. And then lastly, how about this guy? Well, either you subtract 59.65 minus that, or you subtract 93 minus 37.2. You have two ways to do that now. Okay, 93 minus 37.2 will be, that's 55.8%. Okay, now that's for page 3. Let me leave it here. I will take a break. I come back at, let me see. Yeah, I will come back at 6:05. Page 3, the number of times a math student seeks tutoring from Math Center in a week is a random variable X with the following distribution. Okay, we did this routine in test 2, right? Okay, now we want to find, complete this frequency distribution first. Okay, find the average number of times a math student seeks tutoring in a 1-week period. Okay, extend the table above to provide your result below. So let's see what's the total here. This is 60, 70, 80, 95, 5% left. Yeah, confirm that with your calculator in your real test. So Px will be 0 here, 0.25, 0.4, 0.45, 0.20. So when I add, that will be 110, 131.3. So find the average number of times math student seeks tutoring from Math Center in a week period. The average number, so that's the expected value for a student getting help from seek tutoring from Math Center. That will be 1.3. And I need this also, or mu sub x. or simply mu. Okay, let me write the note there. Okay, use expectation of x or mu sub x or simply mu for the notation. Now part B, find the standard deviation of times, of number of times a math student seeks tutoring from Math Center in a 1 week period. So this is for x squared and then px squared. We did this before. So you can think of this as kind of like an extra credit. Then I add this is 0, save 1, 14, 22, 2, so 220. Let me make sure. 0.25 plus 0.8 plus 1.35 plus 0.8. 3.2, not 2.2. So the variance is 3.20 minus 1.3 squared. That is 1.51. So the standard deviation is therefore square root of 1.51, which is 1.22882. Now, how do we use this in real life, right? Now, suppose we have 100 math students. Now, find the probability that 100 math students will seek tutoring from Math Center in a total of 100 times or fewer a week. Okay, so let me call this y now be number of times 100 students. 100 students seek tutoring. From Math Center. Okay, now we don't know if this y is normal or not, but because the sample size is already more than 100, right? Then the probability that y to be more than actually a total of 180 times or fewer, so 180 or less, right? That's equals to the probability that the average is less than equals to 180 over 100. On average, is less than 180. Now, y bar 100, even though the y is not normal, but because the sample size is more than 30, then the mean, the sampling distribution will be normal by central limit theorem. Okay, the mean will be 1.3. The variance will be 1.51 divided by the sample size. Okay, the variance of the original one student distribution is 1.51, right? So divide by the sample size 100. So this will be normal CDF negative E99 up to 1.8 with the mean 1.3, standard deviation 1.22882 over square root of 100. Okay, now this guy here is from square root of 1.51, which we get here, right? And I think the result is 0, but let's see. Normal CDF, negative E99, up to 1.8. The mean is 1.3. Standard deviation is oh no, it's 0.99998. So almost sure is less than 180 times. Now, why do we want to know this? Because then from here we know how many tutors we need to Med Center supposed to hire to help these expected number of these expected students. Okay, so let's say you will have approximately 180 appointments for this 1 week. Okay, 180 appointments for this 1 week. If you have 100 students, what is the probability you have 180 or less appointments? And we see that it's almost 1. So there is no need for me to hire that infinite number of tutors because no, you just need 180 appointments, right? So even if you say that one tutor help a student for 1 hour, right? Then you just need to assign or how to say that? You just need to hire enough tutors that covers 180 appointments. Okay. And almost nobody will complain because almost everybody will get the appointment if so. Now, why do I want to say that? Because then if a tutor can work only 20 hours per week, which is the case for our college, and I know all other colleges also, then actually you just need 9 tutors. Now, in reality, we have more. Some tutors, we need some tutors tutoring more at some time, right? So maybe very early in the morning, you just have 2 or 3 tutors. Around lunch, we have maybe 12 tutors. In the afternoon, we have around 9 tutors. In the evening, we go back to only 3 tutors, like that. Okay, but we will have a total of approximately 180 appointments to do. Now, this also impact how much money the Med Center need to provide to budget for the tutors, to pay the tutors that they hire. Okay, now this cannot be done if you don't know statistic. I'm sorry. Okay, number 5. Assume the assets of credit unions are normally distributed with standard deviation $180 million. So the standard deviation is $161 million. Now, American Credit Union Association surveyed 40 credit unions and find the total assets of these 40 credit unions is $24,300 million. So the sum total asset is 24,300 million. Now, part A, find point estimate for mean. The mean assets for all credit unions. The point estimate for mean assets will be equals to the X bar, which is the total of these 40 credit unions in million over 40. That's $607.5 million. That's the sample mean of their assets. I'll construct a 95% confidence interval from mu. We know the standard deviation, population standard deviation. Notice that sigma is known. Okay, so step 1, best point estimate is X bar equals to 607.5 million. Critical value, Z critical, we need 95% confidence level. Means the remaining 5% will be shared by 2 tails, such that the area to the left of that critical value will be 97.5%. That will be inverse norm 0.97501. Critical value is 1.95996. I happen to memorize that number. Step 2, how about the margin of error? Margin of error is equal to critical value times the population standard deviation is known to be 161. 161 over square root of 40. And this is all in million. 1.95996 times 161 over square root of 40. So the margin of error is 49.89340. So step 3, 95% confidence interval for the average assets of all credit unions will be the best point estimate 607.5 minus margin of error 49.89340 less than mu less than best point estimate plus the margin of error. I get the average will be between 559,006.6066 up to 657.3934 million dollars. Okay. Let me put the 0 so that it doesn't seems to be I make it 4 decimal places. It's actually 5 decimal places. What sample size is needed to determine mu within $10 million? So the margin of error is $10 million and the confidence level is 92%. Okay, means the area in the middle is 92%. The remaining 8% is being shared by 2 tails, each of them 4%. So the critical value will have area to the left, 96%. So the critical value is inverse norm 0.96, 0, 1. But Thomas, I thought the mean is not 0. Well, the mean for standard normal, that's why we use z-score. The mean for standard normal is 0. Standard deviation is 1. I get 1.75069. And then The minimum sample size, therefore, is the critical value squared times the standard deviation squared over margin of error squared. Okay. I got the ceiling of 794.45. Always round up. Always round up. So the sample size will be 795 credit units. That's the minimum sample size so that we can be that accurate. That's for page 5. Page 6. A Gallup poll of 1,024 adults found 413 believe in evolution. Construct a 97% confidence interval proportion of adults believing in evolution. So confidence level, 97%. So step 1, best point estimate. That's p hat is 413 over 1024. That's 0.40332. Oh, so by the way, Q hat, just to prepare the stage, 1 minus that, is 0.59668. Now, critical value, let's see, critical is the area to the left of the critical number will be 97% plus one of the remaining, the area of the one of the remaining tail. 3% divided by 2 is 1.5. So critical value, area to the left is 98.5%. This is inverse norm, 0.98501. I get 2.17009. Margin of error will be 2.17009 critical value times square root of p hat 0.40332 times q hat 0.59668 over 1024. I get the margin of error will be 0.03326, actually 27. Therefore, 97% confidence interval for proportion of people believing in evolution will be the best point estimate less than P less than best point estimate plus margin of error. I get 0.37005 between 37% approximately to 43.659%. Okay. Number 7, a student randomly selects 10 paper bags at a store and finds the mean price is 8.75 with standard deviation 1.5. So the sample size is 10. The mean of the price is 8.75 and standard deviation, that's sample standard deviation. How do we know that's from sample? Because it says that the student finds the sample mean and standard deviation of 1.5. Okay, now assume the data, the price of paper bags is normally distributed. Why do I need this? Because the sample size is less than 30. Okay, now construct a 95% confidence interval for the population standard deviation. Oh, okay. Okay, so even if the sample size is more than 30, okay, the price still need to be normally distributed to apply the model that we learned actually earlier today. Okay, we need confidence level 95%. So it's 95% in between, the remaining 5% being shared by two-tail. Okay, so this is chi-squared right. Chi-squared right is inverse chi, area to the right 0.025, degree of freedom is 9. And chi-squared left is inverse chi, the area to the right is 0.975, degree of freedom 9. This one here I get 19.02277. Later on, I will get 95% confidence interval for population variance. This is 2.70039. This will be degree of freedom times 1.5. That's standard deviation, make it variance to make it squared, over 19.02277 less than sigma squared less than 9 times 1.5 squared over 2.70039. That is 1.06451 less than sigma squared less than 7.49892. But we are not done yet because what they want is population standard deviation, not confidence interval for population variance. So I need to go extra step, right? 95% confidence interval for sigma will be so I apply square root here and apply square root there. I get 2.73842 on the right hand side. While on the left hand side, that's square root of 1.06451. I get 1.03175. Okay, the last page for this test. This type of question, I think it's because it's new, such that I give more points here and there. Okay, let a survey of 40 Math 227 Test 2 scores in Thomas's classes result in confidence interval like this. That's the sample size of 40. Now, if the sigma is known to be 12, find the confidence level. So somebody give you, oh, okay, that standard deviation is 12, sample size is 40, and this is the confidence interval. Can you reverse engineer that to find the confidence level being used? So this is a bit more advanced question. Okay, you don't really see this question in the book, not even in my old test, but this was a common question being asked in university level. Okay, imagine if somebody gives you this confidence interval just to find out that the confidence level is so low, like 70%, right? It's like, hey, you know, it's not trustable, right? Okay, now can we find that though? What is the best point estimate? Best point estimate is the midpoint of the endpoints. So you imagine this, the endpoints is 54 and 62, right? The midpoint, the best point estimate has to be in the middle, right? That's the midpoint formula. How about the margin of error? Well, basically that's the distance between upper bound with the midpoint or the midpoint with the lower bound. Or you can also say that's half of the width of that interval. Okay. Now then, part C, find the critical value. Use formula in step 2. If you use calculator, if you get so used to use calculator only to do my problem, this problem definitely not doable. Okay, margin of error will be Z critical times standard deviation over square root of sample size. The margin of error is known to be 4. Critical value is the one we don't know. Population standard deviation is 12. Is it right? Yeah, it's 12 over square root of 40. Then, based on your ability in algebra, multiply both sides by square root of 40 and divide it by 12. That's the critical value. So the critical value is 2.10819. Okay. Now, part D is only help you to help you visualize that, but the confidence level basically already known. You can compute that already. You see, because if the critical value is 2.10819 here, then this must be the opposite of that, right? Now the confidence level must be the area in between. You see what I mean? Okay, it must be the area in between. So confidence level is equals to normal CDF negative 2.10819 to positive 2.1081901. I get 0.96499. Okay, that's the confidence level. If you really need to round it, then it will be 96.5%. If you need to round it to make it look nicer, that's the furthest you can round it. Okay. Now let's see part D, what they ask actually in part D. Part D, find the area to the left and to the right of Z critical. So the C critical we got earlier was 2.108, what? 19. Now the area to the left, that's a C score, is normal CDF, negative E 99, 2.1081901. That's 0.98249. So the area to the left here is, this guy. Okay, now how about the area to the right? So to the left is the yellow one, to the right is the blue one. Probability that Z is greater than 2.10819. Actually, I can just do 1 minus, huh? Don't you think so? E99, 01. Yeah, I can just move, yeah, I can just use 1 minus actually. Because it should made up to 100%, right? Okay, that will be 0.01751. Okay, now how do we use this result to get the confidence level? Now, if you think about it, the confidence level, which is the area in the middle, okay, is basically the yellow area minus the blue area, which is this part here. This area here is the same to that one. Okay, so I was thinking that the confidence level is the same to 0.98249 minus 0.01751. That will give you 0.96498. Okay, a bit off because of the rounding we had earlier. Now let me do last one. That's the take-home part of, yeah, that's the take-home part of the test. Let me see, that's from fall 20. Let me put it in here. But in your for your test, you will not have the supplement part anymore. Okay, you will not have supplement part later on. Hold on, what happened? Hey, what happened? Why I have some page missing? Huh? Hey. Oh, I see. I know what happened. So there must be some part of the file get into in between. Yeah, you see that. Mm-hmm. Give me a second. So that's 96.95% approximately. 96.5% approximately. That's the confidence level. Okay, this is the supplemental part solution. The length of an adult tuna fish is normally distributed with standard deviation 12 inches. If the first quartile of the length of all tuna fish is 41 inches, the first quartile, what does it mean? Means the area to the left of that first quartile is 25%. Okay, first quartile is the cutoff score for the bottom 25%. Find the C-score associated to that first quartile. The C-score is equals to 41 minus the unknown. Oh, hold on. Find the C-score. Oh, probability that probability that C is less than the C-score is 25%. So the C-score will be inverse norm 0.25. That's C-score, right? Okay, we need C-score. And we know the area to the left is 25%. So the C-score is negative 0.67449. Now use that to find the mean length of all adult tuna fish. We have this population standard deviation, but we don't have the mean. We just know that 1/4 of the tuna fish is less than 41 inches. Now, can we use that to find the mean? The C-score negative 0.67449. That's equals to the 41 minus the mean over 12, right? I use this formula here. So I reverse engineer to find the mean. This is 12 times negative 0.67449 equals to 41 minus the mean. That's negative 0.8, I'm sorry, negative 8.09388 equals to 41 minus the mean. So the mean must be 41 minus negative plus, right? 8.0438. But your math, your algebra should be good to be able to do this though. So the mean is 49 inches something. Find the probability that a randomly caught adult tuna is longer than 60. So at this point, we know that the tuna is normally distributed with mean 49.09388 and standard deviation 12. Okay, now then, what is the probability that the length of an adult tuna is longer than 60 inches? That's normal CDF. 60 E99. The mean is 49.09388, standard deviation 12. The probability will be approximately 18%. Okay, this is where I will stop. That's the solution for your fall 20 Math 227 test 3. Okay, see you then.